Hello, everyone. Welcome back to the AAS YouTube channel. This is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series, and I am super happy to have Hossein Fatheddin and Sedighe Sajadian with us today. Hello, Hossein. Hello, Sedighe.
Hi.
Hello.
I am Hossein Fatheddin. I'm currently in Leiden, where I started my master's 2 months ago here at Leiden Observatory. And I'm very happy to be here to explain about our paper.
So I get to say, well, congratulations, Dr. Hossein.
Oh, thank you. Not just master's. I just started my master's.
Getting there. I know. I'm leading.
Yeah. Thank you. Thank you. Thank you.
Very good. And Sedighe, where are you located at?
Hello, my name is Sedighe Sajadian. I'm a faculty member in the Isfahan University of Technology, Isfahan, central city in Iran. And I'm happy to for this interview and for the talking about this paper. Thank you for interview.
Sure. It's an awesome little paper, and we'll get to it in a bit. And Sedighe, what do you like to do for research in general?
I like microlensing and I like exoplanet very much, detecting exoplanet. I like, for example, free-floating exoplanet detection, about research about this population in our galaxy, and I like isolated stellar mass black hole and their detection with the gravitational microlensing very much, and like to do more research in this field as well.
Cool, very good. Ben Hossein, what do you like to do for research?
For me, my research has been mainly focused on the lensing phenomenon, gravitational lensing phenomenon, especially with the emphasis on gravitational microlensing. I did my bachelor's under the supervision of Professor Sajadian on this subject. But recently, I've also started working on observational and extragalactic astronomy here at Leiden. So I'm planning to do more cosmological and larger scales, to expand my knowledge and research to a larger scale.
Very cool. Very good. Well, thank you. And this is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go grab one. Detecting multiplanetary systems with gravitational microlensing and the Roman Space Telescope. And Hossein and Sedighe, take us away.
The main idea behind our paper is what are the prospects of detecting multiplanetary systems with the applications from gravitational microlensing and the future implementation of the Roman Space Telescope.
Cool.
So we mainly focus on detecting multiplanetary systems with the gravitational microlensing methods instead of the transit photometry or radial velocity methods that has been already used to find such systems.
Okay.
We know from our experience, our solar system contains 8 planets. So it should be very rare for another star to have only a single exoplanet.
Yeah.
But in the case of gravitational microlensing, the planets that have been discovered with the gravitational microlensing method, we have only had about 200 exoplanets detected with the microlensing method. But with using the transit photometry method, we have discovered until now about, let me see the number, about 860 multiplanetary systems out of the 3,900 in total planetary systems. And so the most of the multiplanetary, the system that we can call a multiplanetary system can consist on the minimum from 2 planets. And that's why we focus on the triple lens configurations of a planetary system in our microlensing simulations. And the microlensing is a powerful, very powerful method for discovering dark objects like MACHOs, massive astrophysical compact halo objects, exoplanets, and isolated stellar mass black holes. It's also powerful enough to detect analogs to every planet in our solar system, except from Mercury, which has a very small orbit and a very low mass. It's not detectable with the microlensing method, it's analogs.
Okay.
But it's the only method currently capable of detecting cool, low mass exoplanets and free-floating planets. So this is one of the main advantages of using the microlensing method for detecting planets.
Cool.
Most of the transiting exoplanets discovered to date have been by space-based missions like Kepler K2 and TESS.
Huh?
And the future implementation of the Roman Space Telescope will also gather a lot of more information for the microlensing events.
Yes.
This will completely change. The Roman has been launched since it's expected to deliver numerous amounts of events in its observational seasons, which my instructor, Professor Sajadian, will discuss shortly. And yeah, so since we focus on gravitational microlensing in our paper, it's good to explain a little bit in more details.
Please.
And yeah, on the right side from equation 1, when we have a microlensing phenomenon, we have a gravitational field that bends the light from a source star. In case of if the lensing system consists of two lenses, for example, a binary star system or a star which is a planet,
yes,
instead of a point lens object, we would have the equation number 1, which, as we can see, the deflection angle consists of two separate parts. One part is for the lens number 1, and the second part is for the lens number 2, which we can see the M2 and the distance of that lens object.
Yes. Okay.
Also, the binary lens equation has a complex format, a complex notation, which we can see it was derived by Witt's paper in 1990.
Yes.
And when we expand this complex equation, we will get a 5th-degree complex polynomial in Z, which requires numerical solutions. It's not be calculated analytically. We only can do it with numerical solutions. The situation gets much worse when we have a triple lens system instead of a binary lens system, since it adds another part to the whole deflection angle.
Yes.
We can see in the format of that equation is in equation 3 for a triple lens system.
Let's get a triple going. Yes, there we go. So we got 1, 2, and 3. And let's go.
So now we can see that there is another state, there's another part added to the already polynomial. It makes things a lot harder, which I will explain how we can measure and make simulations for triple lensing events in a little bit time after Sedighe explains the formalism behind gravitational triple lensing.
Okay, take it away.
Okay, thank you for so in the equation 3 we should add another sentence related to the third object, and so we have 3 parts for the deflection angle. The first one is called the host star, and the 2 others are for two planets that's rotating around the host star. And according to this equation, we should have 3 more parameters to our formalism, as can be seen in figure 1 of the paper. And yes, figure 1.
Yep, there's our 2 angles, 3 angles. Yes, yes.
Okay, yes. Thank you. And according to this figure, we have a primary mass and 2 planets around it, rotating around it. For 2 planets, we have 2 mass ratio, Q2 and Q3, and 2 distance. The distance between the planet and the host star is S12 and S13.
Okay.
And if we assume, for example, the first planet at the x-axis, so we need another angle for the second mass with respect to the binary axis with respect to the primary axis, which is phi minus theta in this figure.
Yes.
And accordingly, we have three more parameters for the triple lens system in our lensing formalism. And then so for the binary system, we have just one mass ratio and one distance. For the triple lensing formalism, we have two mass ratio, two distance, and the angle between the binary axis and the triple lens with respect to the host star.
Yes, I'm with you.
And so in the lens equation, as you can see, I think in the equation 3, yes, in the equation 3, we have 3 deflection angle, and we define also for an angular distance, which is the Einstein angular distance as given in the equation 4, and it is a defined angular distance in the lensing formalism, and we define it according to the lens mass, the lens of the host star and 2 planets, all of them. And we normalize the lens equation to this constant length, angular distance, and we reach to the equation 5, which is the lens equation for triple system, for a triple system. And in this equation, we aim to determine Z versus Kc. Kc is the location of the source star projected on the lens plane, and by given the position of the source star projected on the lens plane, we aim to determine the position of its image. The position of its images are given by Z. So we need Z versus Kc in this equation, and the Z1, Z2, Z3 are the location of the host star, host lens, and planet 1 and planet 2.
Okay.
The location of the three lens. And we calculate the lens equation numerically, and by using the inverse reshooting method. The inverse reshooting method was introduced by the Wamsgans for the first time, and we use the same as you can see its paper here, and we use the same method that was introduced by Wamsgans in our calculation to determine the magnification map and the light curve of the lensing due to a triple lens system.
Yes. Okay, cool. I'm with you. 10th order polynomial. Lovely. In Z.
Thank you.
That. Okay.
Before diving more into the simulation details and our results for the Roman telescope, I think we can also discuss the degeneracies that exist in the triple lens equation.
Yes.
As we know, there are many parameters involved in the shape of a light curve, and extracting the proper values for every parameter requires very accurate modeling. And sometimes, since we have a lot of parameters, we can have a degeneracy that would cause the wrong model to be extracted from the actual data.
Right.
These degeneracies include, for example, we have from the lens equation, it includes
whether it's close, whether it's
discrete degeneracy, fourfold closed wide degeneracy, and continuous external shear degeneracy. Which we briefly explain in our paper, which any of these degeneracies can cause the wrong extraction of parameters, the values, correct values from the parameters. But if we can move beyond that degeneracy, we can also calculate the detection probability of actually observing triple lens systems instead of the binary systems. From the papers of Good and Loeb and the papers from Hossein Fatheddin and Gaudi, we know that when we have a high magnification microlensing event, which means the source star and the lens are actually passing very close to each other from behind.
Okay.
And in that scenario, we can expect if the planet, if the lensing star has multiple planets, they would be also discovered, since the lens object and the source object are very close to each other. So the probability for detecting the triple lens, the second planet, is very high, close to unity.
Cool.
But in the weak lensing range,
Mm-hmm.
in the weak lensing range, it's not highly expected to actually observe the second planetary object.
Okay.
And we are even lucky if we can detect one of them.
What happens?
Yeah, let alone the other one, since there's a little bit of a distance between the lens object and the source object.
Yes. Okay. Cool.
The section 3, we discuss microlensing magnification maps, which are two-dimensional planes showing different yeah, exactly. Each point is a solution of the lens equation, which we had on equation 5.
Yes. Yes.
And it gives us a visualization of how the magnification would work in the microlensing scenario.
Okay.
In order to get the magnification map, we use the equation 6, which was introduced by Schneider and et al.
Yeah.
It's the inverse of the determinant amplification matrix gives us the magnification at each point, which is depending on x, the position of the source star. Where the amplification matrix is the equation number 7. Then we can devise a two-dimensional plane, including a lot of rays. Each pixel, let me give the numbers. Every two-dimensional plane is about 10 Einstein radius long.
Okay.
And it contains 800 to 1,400 pixels in each of these two-dimensional planes.
Okay.
We can use the 800 pixels when we have a larger source star. So we have bigger pixels that would suffice completely.
Right.
But when we have smaller stars, which have very small rho star values, which is the radius of the source star, we need to have bigger pixels. So that having larger and bigger pixels requires us to devise each plane into more number of pixels. For example, instead of 800, we have to divide them into about 1,400 pixels.
Okay. Okay.
To get to account for the radius of the source star.
Mm-hmm.
And can we go to the animations?
Sure.
Sorry.
And let's take a look at one of these. Here's the orbital.
Figure 2 on the left. Yeah.
Okay.
Figure 2 shows the orbital motion of two planets orbiting their host star. We can see the configuration of each planet with respect to the star. And
let's take a look at that animation on this one, because I think these are actually pretty cool. And let's pull this up, share screen, and Fatheddin. And here we go. Here's the animation on figure 2.
So we can see from this animation that the two planets are rotating around their host star.
Mm-hmm.
And at the same time, the magnification pattern in the magnification map is constantly changing, going through different changes. We can see their areas changing, we can see their sizes changing, and we can see they become brighter and less bright by their motion.
Cool. Very cool.
This corresponds to different patterns in our light curve, in the actual data that we observe. For example, if we have a larger caustic area for the planetary object, it means that there is a more probable that it can be detected, since it covers a larger area of the two-dimensional plane. And if the caustic is brighter, which happens when the first planetary object is close to the star, it corresponds to a higher level of magnification in our real data, in the light curve data.
Yes.
And from the second animation, we can see that the configuration for the binary setup, the binary star and the planet system, are considered constant, and we only move the second planetary object, or the third lens.
Okay.
And we can see as the third lens goes away from the host star, it becomes very shorter. It loses a lot of area, but it becomes brighter, which means that the probability of detecting that planet when it's far away decreases from when it's closer to the host star.
Yes. Okay, I'm with you.
And this animation also corresponds to figure 4 of the paper.
Yes.
Figure 4 of the paper, where we have gathered the data from every motion of the third lens.
Cool. Okay.
And in the final animation, the third one, we can see how the caustic changes, the second planetary caustic changes as we change the mass ratio of that planet. So as the planet gets heavier, it gets a larger caustic area, which means it will be more probable to detect. And at the same time, it becomes brighter, naturally brighter, which means that we will have higher magnification in that area.
Great. That is awesome. Very cool. People, you can go get these, go check out his GitHub page, Triple Lens Animations. Very good. Very good. Okay, and let me pull back to the article. And there we go. So there's our 3 figures. We just took a look at the animations.
Yeah. And so for every animation, for every figure here, for every magnification map, we can gather the data for how the area changes, for how much the magnification changes at the same time as we change other factors from that triple lens configuration.
Okay.
And these data are visualized in figure 4.
Let's go to figure 4. Oh, this is beautiful. Very nice. Okay.
So plot A in this figure shows as the third lens object goes further, goes away, the area, the magnification increases, which is what we potentially saw earlier. Makes sense. And the plot B shows its area, which decreases.
So one question:
which decreases as we go further.
What are the black dots? Where do the black dots come from?
Oh, the black dots in figure A are magnifications times 10 to the power of 4.
Okay.
And in the right figure, the black dots are the area of the second planetary caustic, which also decrease.
Okay. I'm with you. Okay. I understand now.
And we can also repeat the same information for magnification due to the second planet and the area of the second planetary caustic when we change the mass ratios of objects.
Yeah. Okay.
So the plot C and plot D display there's change with the change of area and the change of magnification due to the mass ratio of that planetary object.
Yes. We got some nice.
And so now that we have discussed the theory of detecting triple systems and the probability of detecting those kind of microlensing systems, we can actually prepare a sample of different possible triple lens configurations to see if they are detectable with the future launch of Roman Space Telescope, which is going to be NASA's next flagship mission in the astrophysics division.
Flashy.
Yeah, we are very anticipating its launch. It's gonna completely revolutionize the field of microlensing, but providing a lot of data.
Yes.
And I think Professor Sajadian can explain more about the Romance Galactic Type 7.
Okay, thank you for explaining the simulation. In the next step, we consider we make a large sample of these planetary microlensing events due to the triple systems, and after that we simulate synthetic data points, and we assume that data points are given by the Raman telescope during its mission, which is 5 years.
Okay.
According to the real Raman observing strategy for the microlensing events, Raman will detect the galactic bulge during 6 observing season, and each observing season will last around 62 days, and 3 of these observing season will be happen at the first years of its mission, and 3 of them will happen at the end of its mission.
Okay.
And during its observing season, the galactic bulge can be observed with Raman, and its cadence will be 15 minutes.
Okay.
It means that the time between 2 data points will be 15 minutes, which is too short, and so it will take a lot of data for these microlensing events, and it is good for detecting triple system. Another point is that Raman will observe galactic bulge in a filter which is called W149, which is the median of the H, J, and the K filters in the standard filter. And so we simulate these data points according to the galactic. Yes, this is a filter of the Raman, and we determine the absolute and the apparent magnitude of the source star in this filter using the galactic boson model, which is a very good model and comprehensive model, and simulated a lot of stars for each structure in the galaxy. For example, galactic bulge, galactic disk, thin disk, stellar halo, and so on. And so we use the Raman, we use the boson model for the determining the appearance and the apparent brightness of the source star as can be seen by the Raman. And also we consider, for example, all details, for example, extinction, and the real distribution of the source star and the lens star. For example, for the source star, we consider the mass, we consider the spatial distribution of the stars in each line of sight from the observer to the galactic bulge in the different field, and we determine their distance. And after that, we should determine the lens object. For the lens distance, mass, and velocity. And we determine the velocity, for example, from a Gaussian distribution for dispersion velocity, and by adding a rotational velocity around the galactic bulge. And so using this distribution, we produce a big ensemble for the source star and another big ensemble for the lens object. And we also add the 2 exoplanets for each lens star.
Yes. Okay.
By determining their mass ratio and their distance. And after simulating their light curve, we add synthetic data point for each light curve to calculate their detection efficiency. If these simulated microlensing events can be detected by the Raman, if the planet can be detected or not.
Okay.
And after that, by considering some criteria, which is a chi-square between the real model and the model by 2 lens, not triple lens, and the difference between their chi-square, we determine if the effect of the third lens can be detected in this data or not.
Okay.
And
good.
Yes, we consider a threshold which is 100 for difference between chi-square between these 2 models. And
threshold.
Yes, and finally we calculate the detection efficiency
Mm-hmm. Mm-hmm. Good.
I think Hossein can explain this part.
Okay, so let's go to figure 5. Let me pull in the light curves for the different ones. Okay.
Yeah, in figure 5, we can see we prepared the 500 simulations for different scenarios of triple lens configuration. And 4 of them are shown in figure 5. For example, light curve 21 corresponds to the red curve shows the triple scenario, the triple data. The dashed black line corresponds to the binary scenario where we only have a hostess star with one planet.
Okay.
So they are binary systems.
Okay. Mm-hmm.
And we can see the difference between the triple curve and the binary curve in the blue curve below the light curve. Yeah.
Okay. Mm-hmm.
So if these peaks, if these data are detectable through the Roman, we will call it we will call that detect to give us more insight into seeing if the Roman is capable of detecting those kind of systems.
Cool.
And we can also see the corresponding magnification maps to the right side of the plot. The upper one corresponds to the triple configuration, which is the red curve.
Okay.
And the one at the bottom only corresponds to the binary configuration. As we can see, we have only the star with one planet.
Gotcha. I'm with you.
So after devising that threshold of between 100 and 500 for the delta chi-squared, we see that the Roman will have an efficiency between about roughly 5% to 17% for detecting multiplanetary system consisting of 2 exoplanets instead of just 1 exoplanet.
Okay.
And that's a very interesting thing to find out, because it promises that the Roman will deliver a very diverse and interesting data for the multiplanetary systems with the Microlensing method.
Cool.
And which was the main result for our paper.
Well, we got the statistics here, right?
Yeah.
Okay. Very cool.
These statistics show the statistical distribution for the parameters involved in our simulation. For example, we have the mass ratios for both planets.
I see.
We have the impact parameter. And we have the separations, angular separations for each lens object.
Cool.
As Professor Sajadian explained in section 2.
Right.
So this shows how we chose our parameters to involve in the simulations.
Very nice.
We use the Markov chain Monte Carlo method to get a clear look at the parameters. Yeah.
Very nice. Very nice. Cool. Beautiful work. Congratulations.
Thank you.
Thank you.
Yeah, and there's a short little appendix here, people, you should pay attention to on some of the simulations. Very nice. Hossein?
This appendix actually explains how the inverse ray shooting method was implemented to create the data that we have simulated for making our conclusions, deriving the conclusions.
Ooh, green serum. Anything that says green serum, you gotta love. Very good. Cool.
Thank you.
And off. Very nice. Hossein Sedighe, thank you so much for walking us through your very awesome article. That's great.
Thank you for having us.
Thank
Sure.
you. Thank you for listening.
Oh, you're welcome. Thank you, Sedighe. And you touched on it a little bit as you were talking, so let me push on it a little bit. Where do you think we go from here, given this article in the forthcoming Roman? Are there other systems? Maybe one wants to consider a system with 7 planets or 4 planets. Are there other telescopes that this might be useful for, let's say, LSST or something along those lines? Is there additional theoretical work that could be done? So just sort of next steps. So where do you think we go over the next couple of years? And let's start with Sedighe. So where do we go?
Yes, I think the next step should be is considering two stars with one planet orbiting around two of them, and it is a common planetary system that are observed by transit, and we aim to study detecting this system with microlensing and by Raman telescope. And we think that the probability of detecting the planet around the two star, a binary system, is high by Raman, because cadence of Raman is only 15 minutes,
Right.
and it's too short to detect this a small planetary signal. And the next advantage is that following up this system by the, for example, by other telescope, for example, ground-based telescope, Danish telescope, and the other telescope, and then that will improve the detection efficiency. If, for example, some part of the light gap is during the gap of observing season of the Roman, and if other telescope can detect this part,
Yes.
it will increase the detection efficiency for this system.
Good. Cool. That'll be very nice. Hussein, got anything, want to add anything to that on the future?
Yeah, as you said, in our paper, we mainly focus on multiplanetary systems that only consist of two planets.
Two planets.
Yeah. So, which is the bare minimum of calling multiplanetary systems. One can also investigate the possibility of detecting triple or four quadruple planetary systems. And it's very simple. You can just add.
Term to that. Yeah.
Yeah, exactly. You need to add the new parts to the lensing equation and calculate their corresponding light curves and the efficiency for detectability of those kind of systems. We are also very excited when the LSST comes online, the data from LSST comes online, which would also, it's in one of its main scientific goals to investigate the gravitational microlensing events in the galactic bulge.
Cool.
So that would also, in the future, help a lot in the future for detecting these multiplanetary systems.
Very nice. Well, I really look forward to seeing this field develop over the next couple of years. It'll be very exciting when Roman LSST comes on, and I look forward to congratulating you on your predictions for triple systems. Very good. Very good. Hossein Sedighe, thank you very much. And that will do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.
Thank you.
Bye.